Okay, all right, again, the structure of the class is pretty weird. It's an 8-week course and we meet half the time. So that means that I should go over this material 4 times as long as I have to do it. So I have 3 hours to talk about what I'm going to talk about, and I really should have 3 to 4 times that time to explain the material for you to have with me to talk about the material. So if it seems kind of rushed, that's why. Okay, so we have 16 weeks crammed into 8, and then we meet half that time. So that's a quarter of the time allotted to learn this material. So that's, if it feels kind of fast paced, that would be why. And then I would think if you took calculus in high school, it would be a full year, be my guess. If you took it in high school, calculus is a year-long course. Here, it's 8 weeks, and we're already going to get into the derivative rules today, and it feels like the semester just got started. So I have to go fast, and really what I consider this to be is an introduction to what you'll be doing this week. It's not really a lecture of this is how you do it. I try to show as many problems as I can, but it's impossible. I know that other instructors treat this class or this sync session completely different. They treat it as an office hour, but I don't feel that that benefits the students much, so that's why I do this. Okay, but I do go too fast, and I do speak too fast, and I go over the problems too fast, but it's recorded. I take pictures, assuming you will go back and look at the material later, because that's the best I can do. And I still can't show all the material because there isn't enough time. So I try to pick specific problems to go over. Another thing about what we're going to do is I've picked out certain theorems, certain definitions from the textbook. Instead of just me flipping through the digital textbook and showing you, I've already screenshotted them. There's going to be an announcement. So I will just refer to the announcement and where it is there, where I'm referring to it, as opposed to showing you the textbook, because there's just so little time to explain it. Okay, I want to spend the most amount of my time showing homework problems. That's my goal. Okay, yes.
In exams, can we use textbooks?
So you will not have access to your textbook while you're taking your exam, because you're going to take your exam through Pearson.
I need a physical textbook.
If you have a physical textbook, if you're taking it in the testing center, they will not allow you. If you're taking it on your own, it would be just like a quiz. So much like a quiz, you could do that as well. But let me warn you, if you need to refer to the textbook while you're taking the test, you've probably already failed. I'm just being honest. Any professor that gives you open book text means that the textbook is useless while you're taking the test, because there's no time. There's no time to teach yourself what the material is while you're taking the test, because the test is time. So that's something that I have had to pay the price on some of my exams when I took sophomore and junior year. I had a theoretical physics course, and it was open book. And oh, could you close that door for me? It was open book, and then I thought, well, this is gonna be easy. And I took the test, and it turned out, unless you just need to refer to some formula or something, you're on your own. So yeah.
I still use it
Yeah.
just to refresh.
And we'll talk more about the exam closer to the exam. All right. And then also, what else can I say? The homework for last week is still due tonight. So you have 2 homeworks, 2 quizzes. I know many of you are still working. That's fine. I'm not going to go over any of the material from last week today. If you want to hang out after class or something and ask me questions, that's fine. But I won't have time during class to do that. All right. So that
another question is, so will all the assignments be logged after 12 p.m.?
Yes. So it's due 11:59 tonight. That's and once that, then we have to move on. All right, so what can we do? Share my screen. So, 2A.
I bought a physical textbook, but I really don't have time to, look at it because like all the assignments
Uh-huh.
takes like time.
Yeah, yeah, yeah. Yeah, it's a very time-consuming class. So my guess is that your homework will take you probably 12 to 15 hours a week to do. Which I think was one of the first things I said when we started class last week. Was just so you know, this is gonna take a while.
So my textbook is on its own on my table.
Okay. Yeah, yeah, yeah. I mean, I still look at the text. Uh, so this isn't posted yet. It'll be posted after class with the video that I'm inside right now. But I have some definitions from the textbook that I've plucked out to do this. And the first one will be what is the derivative? Now, we looked at this formula last week and we used this formula last week, but we called it something different. So we called it the difference quotient. So I call this part. Oops, switch. This part. Why is it hard? This part was the difference quotient. That was something that we used last time. And I said that this was going to be something that we refer to a lot, and here it is. So we talked about limits and we talked about the difference quotient. And what I was trying to kind of get us to is that this is going to be the rate of change for the function. So when you look at a function, let's just look at a straight line. So if I just draw a straight line, the rate of change for this is just the slope. The slope of the line is the rate of change. So you know that the rate of change is slope. Now, what do you do if the function is curvy? What if it goes up and down? What if it's a wave? So if you're looking at a function and it goes up and down, up and down, up and down, what is the rate of change for this function? I don't know. Right? Then it depends on where you are. Depends on where you are in the function. Okay? So the rate of change for something that's curvy depends on where you're looking. I'm going to open a graphing calculator, desmos.com, and I just want to show you a brief example of what it is. So if I have f of x equals something like x squared plus 2. So if I look at this function, the rate of change depends on where I'm at. So this rate of change is negative. And this rate of change is positive. And if I looked right here, it would be 0. So the slope at that point is 0. The rate of change is negative on the left, it's positive on the right. But if you just zoom in, if you zoom into it, if I zoom into this close enough, that looks just like a straight line. That looks just like a straight line to me, if I'm zoomed in. So if I only consider this part, even though the function is quadratic, if I just look at a segment, it's a straight line. And then I can just go y equals mx plus b, the rate of change is the slope. And that's the same for over here. If I just look at a segment of the function, then the rate of change is just a line. So if you go and you look at just a piece of it, then that rate of change is positive and it's the slope of the line. And then there's only one other interesting part about this, and that's the bottom. If I zoom in enough, well, then the question becomes, what is enough? But if I zoom in enough, then it's just a horizontal line, and the slope would be 0. So that part, if I zoomed in enough, would just be 0. So I think the slope of that line is 0, the rate of change at that point is 0. So it depends on where you are, depends on what you are doing, what you're thinking about. And then a real life example of this is you can think of the motion of an object, the speed of an object. If I throw the pin up in the air, there's at some point its speed is going really fast, it slows down and it comes down. That's its acceleration. Or you can think of its position of an arc. You could think of that. You could think of its rate of change in that way. So that would also be quadratic. So when the functions are curvy, you can still think of them as a line if you zoom in enough. Well, how much is enough for that to work? How much do you have to zoom in for that to be a perfect line? Okay, and so that's when Isaac Newton and Leibniz said, well, what if you just went infinitely close? Instead of just going pretty close, what if you just went infinitely close? So what if that change went to 0? What if you zoomed in infinitely? Okay, if you zoomed in infinitely, then I think that point, that is the slope of that line. That's your rate of change. Okay, and if you do that, then you can find the rate of the change for anywhere on the function at all. Anywhere. So you could predict the past and the future. And then that's rocket science, right? So if you want to determine, you spend all this money on this rocket, well, you better know how fast that thing's going, how much fuel it's expending, and where it will be at any given second. Okay, if you're spending trillions of dollars on this, you have to know where it is at any, I mean, theoretically, where it is at any given second. And this is exactly how they did it. So that's the idea, is that if you can, of course, real life is way more messy than math class, but if you can determine this as a function, then go infinitely close. From there, we'll be able to determine what is the rate of change. And rate of change will be speed if it's a physical object. We'll be able to see this. So we're taking the difference quotient, and now we're going to start calling it a derivative. Okay, so there'll be the derivative of the function, and then that is the definition of a derivative right there. Okay, so as the limit of h approaches 0, f of x plus h minus f of x divided by h. Okay, so that's the definition of a derivative. We're going to look at a lot of derivatives today, and then we're going to go even beyond the definition. We're going to talk about what if you have more than one function you're taking the derivative of, and so on. So that's the first one we need. let's look at this one. So for my question 1, it says by determining the derivative of the function, find f prime of a. What does any of this notation mean? So this f prime of x, that was the definition I showed. H approaches 0, f of x plus h minus f of x over h. Okay, so that's the definition of the function. That's what we are supposed to find. And then we want to find it at 8. So x equals 8. That's the idea. Okay. So f prime of 8 equals the limit as h approaches 0 for f of 8 plus h minus f of 8 divided by h. Okay, so I'm plugging in 8 for x. They gave me the function. I don't have to stop the conversation there. So the limit as h approaches 0 of f of 8 plus h, that would be 7 times 8 plus h squared. So that's 7 times 8 plus h squared minus f of 8. What's f of 8? F of 8 equals 7 times 8 squared. That's 7 times 64. 448. Over h. That's the idea. Okay, now I need to keep going, trying to figure this out. But so far I plugged in 8 for x. I haven't evaluated the limit yet, but I just plugged in 8 for x, and I'm going to see what that difference quotient equals. So this still equals the limit as h approaches 0. This is going to be 7 times 8 times 8, which is 64, plus 16h plus h squared minus 448 upon h. Getting closer. So this is similar to what you did for the homework. Now, 7 times 64 is 448. Should be a good calculus teacher and write that we haven't evaluated the limit yet. H goes to 0. So that's 448. 16. It's 112. Plus 7 times h squared minus 448 on h. Okay. And that cancels. Okay. We're almost done. Equals the limit as h approaches 0. H 7h over h. H cancels. The limit as h approaches 0. 112 plus 7h equals 112. So that's by definition of the limit, what it equals. And now I will say, in-person folks, I am not expecting you to take perfect notes. This is being recorded, and I'll just let you know, I'm gonna go too fast. I'm going too fast, but I have to. Okay, so I wanna do this problem again, because that seemed kind of hard. Is there an easy way to do this? It turns out that mathematicians discovered there is an easy way to do it. This is what the question asked me to do, so I did it. I am technically the instructor, so I technically instructed it. Is there an easy way to do it? Yes. Okay, so mathematicians did this for a while, and it was pretty cool, but it was getting kind of messy. And they noticed some trends, some certain things that were happening each and every time each and every time we take a derivative of something that has a power, something happens. So they noticed that if you take the derivative of this function, this is what happens. 7, you bring the 2 down, 2 minus 1. So what am I saying? So after you take the derivative of a quadratic 10,000 times, you will start to notice what happens. The power of the variable comes down and you subtract it by 1. Okay, so it would become 7 times 2x 2 minus 1. Okay, they noticed that that was always true. For this example, for these numbers, that would be 14x. So I showed it legitimately, but now I'm going to show it illegitimate. Okay, so after you do this 10,000 times, you notice, oh, the power is coming down and the power gets subtracted by 1. And if I do that, let's see if I get the same answer. F prime of 8 equals 14 times 8. Is that the same answer? That's a whole lot easier. You can get a hold of that, okay? But every calculus class I ever took, it feels like I took 12 of them. I always had to do everything by the definition, okay? But if I'm only evaluating what number it is, computer doesn't know what method you used. It just knows that you got the right answer. So I'm going to show you both ways, okay? So even in the first question, I am hinting that there are some formulas out there. And that first one is called Theorem 3. So Theorem 3 says the power rule. For any real number k, if y equals x to the k, then the derivative of that, you can bring down the power and then subtract it by 1. So my idea is that what if you had y equals x to the 6th, then the derivative of this, instead of doing the limit, which I can do it both ways, but the derivative of x to the 6th would just be bringing down the 6th. I'm going to bring it down. 6x to the 6 minus 1. Called the power rule, or theorem 3 in our book. So that'd be 6x to the 5th. Okay? And that's a lot easier than doing it by the definition. But in math, we have to know definitions, we have to know theorems, we have to prove things. Luckily, we don't have to prove it in class. Luckily, I don't have to prove the power rule in class today. But it sure is helpful, and it'll speed things up considerably. So that's in the notes already. That's only problem 1. And problem 1 has already kind of told us that there might be an easy way and a hard way to do things for these types of things. I want to show you both, okay? I want to show you by definition, and I want to show you the legitimate. Okay. So the next part is we're given a function. So this is my question to graph the function. Okay, I will assume that you can graph at this point. You're allowed a graphing calculator, and then for your homework, I would probably suggest Desmos.com. I can't afford a better graphing calculator. I mean, it is about as good as it can be. So for just graphing, I'm going to leave that up to you, just to graph the function. But what I want to show is, especially today, how you could take the derivative by the definition, and then also how you could use the power rule. So hopefully that's clear what I want to do. Don't think there's enough screen real estate for me to do it. Maybe there is, probably there isn't. So I'm supposed to find the. Can you see this? So I want to do it by the definition, then I'll show you the power rule, and we'll call it good. All right. So I have f of x equals 2x squared minus 7x plus 5. Now, from there, it wants me to find the derivative by the definition. Definition of the derivative is the limit as h approaches 0 or f of x plus h minus f of x over h. Okay, so that's what I need to do. First thing I need to do is find f of x plus h. So the limit as h approaches 0 of f of x plus h would be 2x plus h squared minus 7x plus h plus 5 minus the original function, 2x squared minus 7x plus 5 divided by h. There we go. Now I need to expand this. Limit as h approaches 0 over 2x squared plus 2 hx h squared minus 7x minus 7h plus 5 minus 2x squared plus 7x minus 5 on h. Forgot a parenthesis. And you can see that if you had to do 100 of these problems, it would be sad. So now you know how I feel. But if you do it, you can do it very quickly. I mean, I was forced to do it, so I can still do it. And I guess that's good because I became a calculus teacher, so it worked out for me. But assuming that's not what you want to do, I want to show you the quick way. But anything that doesn't have to do with h should go away, so may not be so. Goes away, and 5 goes away. Okay, and then we should be able to, as we did last week, if everything goes right, should be able to factor out h, cancel the h on the bottom, and then let it go to 0. So the limit as h approaches 0 is 4x plus 2h minus 7 over h. H cancels, and you're going to get 4x minus 7, and that's exactly what it is. Okay, so that's how you do it by definition. My whole point to this is even though the homework asks you to do it, you probably don't want to do it. Okay, so there's another way. How can you do this more efficiently? The power rule. So by theorem 3, and that's what we have here, we have a quadratic. So by theorem 3, I can take the derivative directly just using that idea. And that really makes my life easier. So going over here, I just need to practice bringing down the power and subtracting by 1. So this will be 2 times that 2, and then 2 minus 1 is just 1. And then here, it's kind of like a silent one. We have negative 7x to the first. So you bring down the 1 and you subtract it, it just goes away. So that'd be minus 7. And then the 5 didn't have an x, so it would just go away. It's a constant, so it just goes away. So I would be left with 4x minus 7. I needed less than 1 line to be able to do it. I needed almost a whole blackboard to do it by definition, and I get the same answer. But they are technically the same. They are technically the same. So may I motivate you to learn the power rule? It's going to be so much easier. Okay, just understand what the definition is, how it connects to it in theory, but in practice, power rule. In practice, power rule. Will there ever be a time outside of college that you would need to know the definition of a derivative rather than the power rule. I would say it's not possible, but it's unlikely that most of you that went into engineering that you would need to use the definition. And if you did, by that point, you would be okay. So definitely learn the power rule. So theorem 3 is really saving some sweat on that graph. That's true. And like everything in brief calculus, I am not going to justify it with a proof. I think that would be hopeless to try to prove the textbook in this course, so we'll leave that to future calculus courses. So we need to know both, but I want you to lean towards understanding that power. Again, what am I doing? I'm bringing down the power, and then I'm taking the power minus 1. So that's what we're going to practice today. Is there any questions, comments, or concerns about how I did this with power rule? Again, what I want to do is I'm bringing down that 2. 2 comes down, and then it's 2 minus 1. I'm going to subtract 1. Minus 7. Technically, there's a 1. That'd be 1 minus 1, which is 0. 5 just goes away because it's a constant. So you get 4x minus 7. Power rule saves us a lot of work. And if you believe me on the power rule, then wait till we get to giant functions where it would be, I don't want to say impossible to do it by definition because that's not true, but we'll say difficult. Not impossible, difficult. Okay, so that's the idea. I want to show this one, not necessarily the graph of it, because we talked about that last time, but how you could find the derivative of something like this, either with the definition or the power rule. I say even the power rule is kind of confusing. Okay, so the function I'm looking at, and it's going to come up a lot today, is something like 1 divided by x. The issue with 1 divided by x is it has a restricted domain, so that's trouble. We can't divide by 0. If we allow ourselves to divide by 0, we start getting nonsense like 2 equals 5, and that's a big problem. Another thing is, what do you do? I've only talked about the power rule, so what's the power of 1 divided by x? So I had x squared. That wasn't so bad. I just brought down the 2 and subtracted 1. What's this? This is 1 divided by x. So I don't know how to do this. Okay, yeah, I'm stuck. Unless, remember algebra. So this is kind of like the 4th semester of algebra. This is kind of how I think about this class. It's like 4th semester algebra. And all those other semesters, there was all this converting functions with exponents. I know they do that a lot. And I want to recall that 1 over x is the same thing as x to the negative 1. Now it has a power. And if it has a power, that's good, because now I can use a power rule, and I don't have to use the definitional limit, even though the homework asks me to. And I'll do it if you want me to, but I'm just showing even the power rule was a little tricky, because I had to know that. So x to the negative first is equivalent to 1 divided by x. So if that's true, then I can use the power rule. So by theorem 3, I can bring down that power. So I'm going to bring down negative 1. I'm going to have negative 1 minus 1. Subtract 1 away. So that would give me negative 1 times x to the negative 2. And I could rewrite that as negative 1 over x squared. I could replace that exponent back into the other version as if I never did change it out. So that's calling upon, I think even my 023 class goes over that, but I'm not assuming that you took 023 last week. I'm sure you need a review, but I wanted to bring up that even if something's in the denominator, you can exchange that for an exponent That makes our life a lot easier. So you can see I can get the derivative by just using the power rule, and I don't have to use the definition. Okay? So by definition, what I mean is I'd have to do the limit as h approaches 0, f of x plus h minus f of x divided by h. Which you absolutely can do, and I know you can do it because you finished last week's homework. So that's clear. The limit as h approaches 0, 1 over x plus h minus 1 over x divided by h. First step is to reduce that h in the bottom. And once you do that, we need to let it go to 0. Does anyone want me to finish by definition? Do you want to see it? So the limit as h approaches 0, let's do a little cross multiplication. So that's just me doing, I haven't done anything yet. I'm just rearranging terms so I can find it. And then I would have x minus x, that would be negative h. Yeah, there it is. Okay, so I see it, now I gotta show it. The limit as h approaches 0, x minus x, so I get minus h over x plus h over h, and that h is going to cancel. Now if I let it go equal to 0, I get negative 1 x squared. That is to say that by definition, we'll give you the same thing as power rule. So I personally am going to choose the power rule, which is theorem 3 in the textbook. So we can use either. So I would, if I'm just answering homework questions, I want to use the easier one to do, especially if it's something like this. Okay, still a lot, and let me show that power rule one more time. But are there any questions, comments, concerns, complaints, or criticisms so far about definition of the limit or the power rule and how I'm using it? Is it clear that, I mean, you're going to see it over and over and over again today. But is it clear that they are the same thing? Is it clear how I'm using the power rule? The power comes down, previous power gets subtracted by 1. That's something we need to know. I kind of used theorem 4 in that previous problem when I took the derivative of a constant. And I take the derivative. What is the rate of change of the number 5? How much does the number 5 change? It doesn't change at all. The rate of change for the number 5 is 0. Doesn't change whatsoever. So I kind of used theorem 4 there a little bit. But the rate of change for a constant is 0. There is no change. So something to keep in mind. But we're going to, even today in class, we're going to see a lot of this. Okay, so I'm going to go to question 5 and see what I might learn. So this says find an equation of the tangent line to the graph f of x equals 2 divided by x at the point 6, 1/3. What on earth is a tangent line? What on earth is this homework talking about? What's this guy talking about? Tangent line. What does that mean? So, oh, did you say it? No. Okay. The tangent line is going to be the line that touches the point and has the same slope of the function at that point. Okay. So I'm going to show you in a few different ways of what that means visually. Let's see, do I have a tangent line here? Sure hope I do. Got everything else. Lost the definition. Uh-oh. Missing. Here it is. Okay. So I got it from the summary. A tangent line is a line that touches a smooth curve at a single point, a point of tangency. See the figure in the middle of page 138 for examples, tangent line. So visually, let's see that it's a tangent line. Look at an easy function. See how this works. So I have f of x squared here. So there's infinitely many tangent lines for this. And the way we find that, well, I guess even what it just looks like, is imagine that there is a line that just touches this line, but has the same exact slope. It's not very good. Something like this. So a line that's infinitely long, that if you give me a point, it just touches the function, but has the same slope as the function. So the slope is the same at that point, but it is an infinite line, okay? The tangent line is a line. It's y equals mx plus b. It has the same slope as the function at that point, okay? So what am I talking about? So the tangent line is a line, okay? Y equals mx plus b. So here I have a line, it's infinitely long, okay? Tangent line just touches the function at a particular point. They gave me the point. They're going to give me what point that happens. Here I just picked one, okay? But the homework will give us a point. The tangent line has the same slope of the function at that point. Tangent line slope equals f prime of x at that particular point. Let's call it x0. So it's the rate of change of the function at that point that has the slope. Okay, so that means I need to know what is the rate of change of the function at that point. That would tell me the slope. If you give me a point, then I can find you a line. That line would be a line that just touches the function at that point and has the same slope. That's the idea. Okay. I think tangent means to touch, like just touching that function. So that's what it means. But it have the same slope and it just touches the function at that point. Why on earth would anyone want to study this? Well, imagine that you're spinning really fast in a circle and you let something go. That tangent line, that's the line in which the object will fly. Okay, so you can imagine any kind of rocket science, anything like that, that's going to come out to play. So if this thing is spinning around, you let something go, it's a tangent line of the curve. That's where the object goes. That's the direction. That's one silly example. Okay, but you can come up with a bunch of business examples of your, cost, revenue, product, or profit, that kind of thing. So that's the idea. Now let's get back to the homework and see how we would find something like this. Okay, so find the equation of the tangent line of the graph of f of x equals 2 divided by x at the point 6 1/3. Okay, so they gave me a function, they gave me a point. They want me to find the tangent. First thing I have to do is, what is the slope of the tangent line? What is the slope? The slope of the tangent line is the rate of change of the function at that point. It's the rate of change. So I need to find the rate of change. How do you do that? We'll take the derivative of the function and we'll find what is the rate of change of the function at that point. So I'm going to call this 2 to the negative first, and I'm going to use my power rule and not use the definition. So I'm going to bring down the negative 1 here. Okay. So I would have negative 1 times 2 x to the negative 1 minus 1. Okay. So by power rule, that's it. So that's negative 2x to the negative second. If I want to rewrite it, I can. So that's the derivative, negative 2 divided by x squared. So that's f prime of x. That's the derivative. It's not what the question is, but it's a good start. What's the rate of change of the function at the point? So f prime of 6. My problem is interested in that point. It wants to know when x equals 6. So I'm going to plug in x equals 6 and see what happens. So that'd be negative 2, 6 squared. So I think that's 1/18. Okay. So my first step was I need to find the rate of change of the function at that point, at the given point. So I took the derivative and I plugged in x equals 6. That's all that happened. This is the slope. Slope of tangent line. Look, it's the slope of the answer. You can see the answer. It is the slope. Okay, that's the slope. So we have the slope of a line. We have a point. We need to find the line. So I have m equals negative 1/18, and I need to know y equals mx plus b, which means y equals negative 1/18 x plus b. The only thing I don't know is the y-intercept of this line. I don't know what it is. So how do you find it? You could plug in your point. So if I plug in my point into this with that particular slope, it would tell me the y-intercept. Okay. So I take this point, I'm going to plug it into my line. And that would tell me the y-intercept. Okay. What color? Let's see. So that's 1/3 for the y equals negative 1/18 times 6 plus b. Okay, well, just for the arithmetic, that turns into a 3, so I have 1/3 equals negative 1/3 plus b. 1/3 plus 1/3 is 2/3, so I think b equals 2/3. So I think the slope is negative 1/18. I think the y-intercept is 2/3, and that is the line of the tangent line. I'm sorry, that is the tangent line at that point. What on earth did I just solve? What did I just find? They asked me, what is the tangent line at this point? What is the tangent line at this point? I can guarantee you, without fail, any calculus midterm is going to ask a question just like this. No matter where you take it, anywhere in the United States at any level, it's going to have find the tangent line. And if they don't have it like this, they'll have it in an even more complicated way. But they'll have it in some kind of way. It is fundamental that we have to do. So I want to explain it again. What is the tangent line? It's the line that just touches the function but has the same slope of the function at that point. So how do you find that? First, we find the derivative. We plug in the point. Then we find the slope. Then we find the y-intercept. So what color haven't I used for this problem? first find f prime of x. Second, f prime of x 0. I'm going to call it the point at which they give me. They give me some x value. So I found f prime of x naught, so some given point. This time it was 6. This is the slope of the tangent line. Okay, and then third, y equals mx plus b. What you can do is you can plug in what you know now. Now you can plug this in and find your line. So they have some y that they gave you. You just found the slope. Just found that. And they give you some point. Solve for b. It's easy as these dozen steps. If you can do these dozens of steps perfectly, you can get it right every time. But it just takes practice to do it. And there's all kinds of applications for this. That's why it's drilled into every head university student, because there's all these applications of the tangent line. If it's, oh my gosh. I mean, before, this is all based off of primarily in the 60s when they were teaching rocket scientists. I'm sorry, even in the 50s. They were teaching rocket science to high schoolers or trying to get them prepared because all of a sudden we need all these rocket scientists in the country. That's where it came from. But it has all these other applications too. It doesn't have to be rockets and slingshots and that kind of thing. I mean, it can be more abstract, like your business or energy. Even in computer science, there's some concern with how much energy these servers are consuming, or I mean anything that's curvy. This is going to work. Okay. There's probably infinite amount of examples that that's true, but I think primarily you guys were business and business managers, right? And business or somebody was advertising or something. Business. Okay, and then you were business. So in-person folks, 100% in business. So yeah, even though it's abstract, like this is our profit or whatever, you can see if we just kept going at this point. This is what it would be. And lines are easy to understand and easy to explain. So if you take out all of the messiness of the ups and downs and you just go with a tangent line, it's easy to convey meaning to it. But I don't think that was the original intention of the math. But if it's true for all things that work. Okay, this one is much more academic. List the points on the graph which the function is not differentiable. Hold on. Hopefully I can pull up a bigger picture for everyone. Okay. Let me just visually, because that's all they gave me, just visually where are we going to have some problems. Looking here, looking right there, I noticed that the graph is split. It's going to infinity over here. It's coming from negative infinity down here. That's a problem. And that's coming from something like this. Okay, so the function is split. Last time we talked about the limit not agreeing. Okay, a derivative is a limit. So it's not agreeing. The limit's not agreeing on either side. So certainly the derivative would, because the derivative is a limit. So it's not going to agree. So right there, that's going to be a big problem for us. So I would say whatever this x1 is, that's an issue. Okay. Let's look at another one that might not be as obvious at this stage. And it probably won't be. If you go on the calculus, it'll become a giant issue. The first semester, it's not as much. Over here, we have something that looks kind of like a corner piece. If you take calculus your senior year, it seems like you only focus on the corners because they fall apart there. So then senior year, you focus entirely on the problems. But we kind of go, okay, it's not differential there because it's infinite. There's an infinite corner there, so it's hard to figure out what the definition is. You could also imagine that the limit is going to fall apart if you have something that looks like this, right? With those corner pieces, that's going to be an issue. What a real life example of that would be, I guess in real life, like if you guys are business, I'm assuming you're gonna study like what customers or product demand, that kind of thing. I would say you just have limited data, because if you were infinitely close with data, you would get rid of the corner. At least that's where my head's at this afternoon. The only time I ever came across this outside of math class was in an electricity and magnetism course, and it was if you got the corners of two metal plates and it made an electric field, it was pretty much impossible to theoretically determine what would happen at that corner. It's going to cause some odd behavior or something like that. If you think of a sound wave, going in here, definitely going to be some ricochets, and it would be hard to figure out what's going on there. So outside of math class, that's the only thing I can think of that would. But just by the definition of a limit, that's going to be an issue. So let's say no splits here and no corner pieces. That's going to be a problem. Now I ask you, what about here and what about here? Is that a problem? So at x2 here, there's a hole, but the limits would agree, right? That's what we talked about last week. The limit is agreeing on the left, the limit is agreeing on the right, so that looks fine. But it can't actually evaluate at that point. Okay, over here, the limit agrees on the left, agrees on the right, but I can't actually evaluate at that point. So it seems like the limit exists for those points, and the derivative is a limit. So we need to make sure that that works. But would it work if you can't evaluate at the point? And I argue that that would be an issue, to be able to evaluate. So not only does the limit need to exist, but so also you should be able to evaluate it at that point. So this is why I've chosen this selection. So no corner pieces. Please, please, please don't come up with a function with corner pieces. I still have nightmares about that. Okay. And I mean, you can imagine with electronics, if you have fields going over each other, that's going to be a problem. You're going to short it out. Pretty much the short. Okay. Or if you think of a mirror and you point a laser in the corner of it, if there was a mirror that was a corner, what would happen with that ricochet? It would be kind of a mess. If it was infinitely close, I have an issue there. So that's my thoughts on what is differential on that problem. Okay. This is a piecewise function, and that's another issue that we need to watch out for. So again, limit has to meet the definition of a limit because the derivative is a limit. But you also need to be able to evaluate it at the point. And no corners. There's no corners. But let's see what happens. So we have f of x equals x squared plus 5. X is less than or equal to 3. And f of x is 3x plus 5 for x plus 3. Well, I can tell you for anywhere but x equals 3, we have no problem. The limit exists. The derivative exists. There's no problem. I have a feeling that the homework is going to be only interested in one particular point, though. It just happens to be out of the infinite points they could have picked, they picked where the problem is. And that's, is it what happens at x equals 3. It's the only point out of an infinite amount of numbers they could have picked, but that's why they picked it. So what is it continuous at f, or is the function continuous at x equals 3? So even without graphing it, I claim you don't have to. You can just look at the piecewise function and see what happens. If you plugged in f equals 3, do you get a point? Yes. So you can evaluate it at that point. So that's good. Okay. If I go just a little bit less than 3, it still exists. So that's fine. If I go just after that, I still have an answer. I could evaluate this at just after x equals 3. So 3.00001. I can evaluate, no problem. I can go just after 3 and still get something. So I can evaluate it on either side, even at x equals 3, no problem. I claim, without even graphing, that this is continuous, because the function exists on either end. That's not a problem, okay? So I claim it is continuous. Is it differential? So if it's differential, then it has to meet the definition of a limit. Does the limit work? Okay, look at this. The limit as x approaches 3 from the right, the limit as x approaches 3 from the left. This is like last week's homework. Will it meet this requirement? Are they the same? Are they the same? I don't think they are. So if I go from the right, I get 3x plus 5. That's what, 9, 14? If I go from the left, I get, I'm sorry, I think I said it backwards. So that's 9, that's 14. If I go from the right, then you also get it. Now, what if you go just before that? Does it work? No. So I think the derivative is going to be, it's not differential at that point. If you picked any other point, it would work. But they just coincidentally picked x equals 3. So I do not think this is differential. If we want to graph it, we could, and you can see that it's going to have different rates of change at those points. Okay, so I don't think it's differential on either point, but it is continuous, and you can evaluate it. Okay, so a function can be continuous and not differential. If it is differential, then it must be continuous. It doesn't go either way. Let's go to some problems where we can do some work here. All right, I think this is closer to where I was supposed to introduce the power rule, but I introduced it early. So if you have something like y equals 9x, and you want to find the derivative, that's what this means here. dy dx comes from the change of y over the change of x. Okay, that's where it's coming from. So from delta, and then from your high school days, it's the slope. It's the rate of change. Okay. Don't show any of my calculus teachers that I wrote it this way, but it's kind of true. Okay, it's the rate of change infinitesimally close at whatever point you're talking. So it went from the change to delta to d. That's where we're getting this. So this isn't quite right, but I'm just trying to show this is similar to slope. But the issue is you'd have to be y2 and y1, x2 and x1 have to be almost infinitely close for this to be true. That's the limit as h approaches 0. Business. Okay, so by the power rule, what's going on here? Y equals
9x.
What is the exponent of the x then? Yeah. It's like one of my students called it a silent one. There's like a silent one. I don't think I could say it any better, so I just repeat what they said. So it's like a silent one. If I use that power rule, then what I'll do to find the rate of change of y with the rate of change of x, I'll just bring the 1 down. So 9 times 1, x to the 1 minus 1. So the power rule tells me I have to bring it down by 1. So that's 9 times 1, which is 9. And then x to the 1 minus 1, that's 0. And from algebra, we learned anything with the exponent of 0 just goes to 1. So I think the rate of change for the function, really at any given point, is 9. The rate of change is constant to 9. So that's the power rule that I am invoking. Theorem 3. Somewhere. Oh, theorem 3. So I cast the spell of the power rule. Don't hesitate to ask me questions or stop me. Is there any questions, comments, concerns about how I figured out that the answer was 9 for that? Don't hesitate to ask me math questions. Okay. Same idea, harder problem. Okay. Same idea, just harder problem. Y equals 20 times square root of x. It's the same thing as y equals 9x, except we just have to remember more algebra. So y equals 20 root x. Anyone remember what the exponent is for a square root of x? X to the 1/2. X to the 1/2 is the same thing as square root. So square root of x is the same thing as x to the 1/2, cube root, x to the 1/3, fourth root, x to the 1/4, so on. And then we could even get harder. We could do that would be a better example. All of those. So we need to know those exponent rules to be able to convert this to a problem we can use a power rule, because the power rule is so much easier to deal with. So it might be worth reviewing this week. We have a week to review it for your exponent rules, because if you know those, then you can convert these things. It makes it so much easier. So I claim 20 times the square root of x is the same thing as 20 times x to the 1/2. And if that's true, then we can just use the power rule to do this. So what's going to happen? The 1/2 is going to come down. The 1/2 comes down. So I have 20 times 1/2 x to the 1/2 minus 1. And that's a lot easier than doing it by the definition, but by the definition, of course, it would be equivalent. So we have 1/2 of 20, which is 10. That's no problem. So I have 10x to the 1/2 minus 1. So 1/2 minus 1 would just be -1/2. So that becomes -1/2. If you have 50 cents, and I take $1, now you have -50 cents. Yeah. And then if you want, we can convert this back without the exponent. We can say 10 divided by x. Just converting it out of exponent. So it makes it a lot easier to be able to use the power rule. do that. Any questions, comments, concerns? Complaints or criticisms? Future notes of how I did that. It will come up a lot today. Because I need to use the exponent rules to be able to simplify the calculus problem. Online folks, don't hesitate to stop me if I say something wrong or if you have a question. Yes, they're over in my office. They're in the adjunct office. Which is good. I was relieved. Yeah. I was like, oh good. I'm glad they're not banging on the we don't have Santa Claus banging on the ceiling anymore. Helps. I heard some other people complain about that noise. It was pretty distracting for sure. Pretty hard to think about anything other than banging on the ceiling while you're being drilled limits in your head. Right. So we have y equals 8x divided by 7. I want to find the derivative. So as always, I want to somehow convert this to an exponent. Even though it's probably obvious, I'm going to say that 8x divided by 7 would be the same thing as 8/7 times x. And that the exponent on this is again like a silent 1. So it's understood that there's a 1 there. So if I take the derivative of this function using the power rule, then I would have 8/7 times 1, x to the 1 minus 1. 1 minus 1 will go to 0. So the variable would go away. So you have 8/7. Maybe it's totally obvious that you can convert it there, but I thought worth mentioning that you don't have to go 8x times 1/7. I mean, it's just a lot easier. Just consider it as a coefficient with a variable. It makes it a lot easier for me anyway. Okay, let's see what else we got. If f of x equals 5x squared minus 6x plus 4, find f prime of 1. What is f prime of 1? F prime of 1. F prime of 1 is the derivative of the function evaluated it at 1. Okay. So remember, f prime of x was the limit as h approaches 0, f of x plus h minus f of x over h. Okay. If they want f prime of 1, limit as h approaches 0, f of 1 plus h minus f of 1 over h. But I don't think this computer is smart enough to figure out whether I use the power rule or the definition of limit. I don't think it's that smart. So I'm going to use the power rule, even though I could use the definition. So I think the power rule is equivalent as finding definition. So since this is a quadratic, I could find f prime of x just by using the power rule. So that's just exploiting the exponents there. So I have 5x squared. So if I bring that 2 down, it's going to be 5x to the 2 minus 1. So of course it's just 1. But I want to show where this is coming from. And that 6 there is going to be, I'll take the 1 down. Then you'll have x to the 1 minus 1, which is 0. And the 4 will go away. That's theorem 4. Theorem 4 is that 4 is going to go away. The derivative of the constant is 0. The rate of change of constant is no change. No change. So plus 0. You don't have to write that, but I'm going to. Just so you see that if I take the derivative of 4, it's just 0. It's just going to go away. And then I should just rewrite this. So I get 5x minus 6 is the derivative of the function. Okay, but that's not what they wanted. What did they want again? F prime of 1. So I plug in 1 for x. So that means f prime of 1 equals 5 times 1 minus 6. Is anyone going to call me on my mistake?
Forgot to bring your 2 down.
Thanks.
Multiply by 5.
Is that Becky?
Yes.
Thanks, Becky. Yes. Okay. I think I said it, but I didn't do it. And that counts as not doing anything. Plus 0. That's better. 10x minus 6. So that is the derivative function. I'm pretty sure. And then f prime of 1 equals 10 times 1 minus 6. Banging up there again. They must be back. 4. Thank you, Becky. So it's easier if you do it right the first time. Forgot to bring that up too. So be careful of that. Save the picture. So if you're looking back, it's correct. Took the mistake away. Okay. Is it clear now how I got 4? Especially since I made a mistake. Is there any questions where 10x minus 6 came from? Any questions how do I get 4? Any questions why did I plug in 1? Anything like that? $29. For what point on the curve of y equals 7x squared minus 8x is the slope of the tangent line equal to 48? Whoa. The slope of the tangent line equals 48. What was it we were going on about tangent lines? So tangent line was the line that touches the function, has the same slope as the function at that point. And I said they always have to give you the point so you can find the tangent line because they have to tell you where it is. But they didn't do it this time. This time they told me the slope. So they said the slope of the tangent line equals this. So I'm kind of doing it backwards. So the slope of the tangent line is 48. Right, so I gotta remember, what did I do before? So to find the tangent line, I took the derivative of the function, evaluated at the point, and that told me the slope. But they're telling me the slope now. They're saying the slope is this. So I gotta do it kind of backwards in a way. So let's see what we can do. First step is I'm gonna take the derivative of the function, see what that equals. And then I'm gonna set it equal to the slope, because they told me what the slope is, and then I can find the point. So it's all backwards now. Okay, so they gave me the function minus 8x. Okay, so I need to find the derivative of this. I'm going to use a power rule, of course. So derivative, I'll just call it y prime. If I bring down that 2, don't let me mess up this time. So I bring down the 2, so it's 7 times 2, x to the 2 minus 1, which will just turn into 1. Minus 8 times 1, x to the 1 minus 1. Don't have to show me that step or anything like that, but I want to show it to you, and hopefully I'll do it correctly. That would be nice. 7 times 2 is 14, minus 8. So I think that's the derivative of the function. That's not what they asked. They said, at what point? So they're kind of asking me that other question, but backwards. They gave me the point in the previous tangent line question. Now they're giving me the slope of the question. So this is the derivative. This is f prime of x equals 14x minus 8. They said the slope equals 48. So if the slope equals 48, I'm going to set the derivative equals that and solve for x. So that'd be 14x minus 8 equals 48. So I'm setting it equal to the slope. That's what they said it equal. Now I can solve for x. Add 8 to both sides. That gives me 56. 56 divided by 14. Said assuredly 4. Okay, I've got the x coordinate. I've got the x coordinate of where this happens. Now I need to find the y coordinate. Where do I find the y coordinate and find the x coordinate?
Plug in the 4.
Plug it back in. So I'm not exactly right. I'm going to plug x equals 4 into the original equation, right? Okay, so x equals 4 is going to go into 7x squared minus 8. I don't know how well that shows up. Here it is. So that's 7 times 16 minus 8 times 4, 80. Santa Claus is back. Yeah. Roof stomping.
And I spoke too soon.
Yes, we did. I was like, oh, good, it's over this week. They're in the adjunct office. That's okay. No, they're back. All right. So x equals 4, y equals 80. So that is the point at which the tangent line slope is 48 is the point for a, not the interval, but the point. Questions, comments, concerns, complaints, not about the roof, but about this problem. So it's like the other question, but it's solved it backwards. Before they gave me the point, found the slope. Now I found the slope and then the line. Here they gave me the slope, so I can find the point at which that happens. Okay. And of course I could find the line, but fun do it. And I thought it might be good if I do at least a couple application problems from this section. I'm not going to do all of them, of course, maybe a few. So problem 31, the equation is given. Hopefully I don't have to find it myself. R of V is 6,400 divided by V. Can be used to determine the heart rate R of a person whose heart pumps 6,400 milliliters of blood per minute in V milliliters of blood per beat completes part A through C. Okay. Part A said, find the rate of change of the heart with respect to V of the output of the beat. Okay. So I need to find the derivative. And the first thing I want to do is rewrite this with exponents, because then I can use the power. That makes my life so much easier that I don't have to do it by definition. So if I take the derivative of that, I can use the power rule. Do that, it'd be 6,400 times -1, V to the -1 minus 1. Should be -2. 6,400 V to the -2. So I brought the exponent down, which is -1. I subtracted 1, goes down a power. This is what I think the derivative would be. So I think derivative, first derivative, is -6,400 divided by V squared. Okay. Now part B, find the heart rate at 90 milliliters per beat. So my question is to you, do we plug that 90 milliliters in the original question, in the original function, or in the derivative? Let me look at it again. Find the heart rate at V equals 90 milliliters per beat. So am I plugging it in the original, or am I plugging it in the derivative? I think I'm plugging it in the original for this question. Let's see if I'm right. So if I do that, I would have 6,400 divided by 90. Is that right? Is that wrong? So I think it's 71.11 beats per minute. I could imagine that's confusing. It's kind of confusing to me because the rate of change is something like miles per hour. And then we're looking at heart rate, rate of change. There's all these vocab words thrown off at the same time. So I thought it might be good if we went over it together instead of just assuming. Now I think the second part asks me find the rate of change. So if it's okay, I'm gonna take this away. It says find, find the rate of change at that point, okay? So that would be R prime of 90 equals -6,400 divided by 90 squared. What does that equal? -6,400 divided by 90 squared is something like, and of course it just keeps going on and on and on, but it's something like that. So the rate of change is negative. Let's just, I mean, between me and you, let's just call it 0.8 beats per minute per milliliter. So that's the rate of change, which is like the speed. That's the idea. Since that middle one kind of reads like rate of change, and then the third one is definitely rate of change, you need to watch out for that. But this is not a medical class, it's a calculus class. So I'm more concerned with turning it into exponents, taking the power. That's my primary concern at this moment, just being able to do that. Okay. Oops.
One question.
Yeah.
So how did you determine which equation to use?
For,
In the previous question.
yeah, so, the first one says find the rate of change, so I did that. The second one says find the heart rate. So finding the heart rate, well, let's see what this says. This function can be used to determine the heart rate. So, how do they do it? I had to reread it a couple times because rate of change is so close to find the heart rate that it took me a minute. So the heart rate is, but this is to determine the heart rate. Then the third part is find the rate of change, and I know that that's the first derivative. So that's how I determined which ones to use. Here's where we're gonna start getting in trouble. And then that will lead us into the second half. So this is gonna bring us right into the break. So we have this big giant function that's really ugly. Let's take the derivative of it. So there, as with many things in math, there's many ways to look at it and many ways to tackle a problem. One way would be to use exponents, but even that is not going to save us completely. Okay. So for online folks, if you're still halfway listening to me, I ask you to come back to me fully, and I want to show you this problem because we're going to go over kind of the next step of difficulty. So we want to take the derivative of the given function. What's the issue? Now we have, I would say, almost a function over a function, or an expression over an expression, binomial over binomial. And we don't know how to do that. We only know how to do them individually. And we talked about that with the power rule. So we know how to take care of them individually, but how do you take the derivative of something that's a ratio? How do you do that? One school of thought is that you could convert this to 2x minus 5, 8x plus 7 to the negative first, plus x cubed. But that still doesn't completely save you. But that's one school of thought. Okay? Is that you can say the thing in the denominator could have a negative exponent, and then you have to try to do that. But even this is going to be a problem because now we have a function times a function, and we don't know how to take the derivative of that. So that's an issue too. So we're kind of stuck at this point. We really don't know how to do it. So we're gonna have to look in the book, see how you do it. So I pulled this. This is what we want. Okay. This is one of these formulas that you're going to have to use so much, you're gonna have to memorize it, okay? We'll talk about formula sheets and all that closer, but how about today, we're just worried about you finishing the homework. So if you write any notes at all, please write this formula down. This is gonna be the quotient rule. It's gonna be our way of solving something like this. And it says that if you have a function over a function, something like this, that this is the formula which you could use to take the derivative. Okay, so if you have f of x over g of x, okay, and you want to take the derivative of that, then the derivative is f prime of x times g of x minus f of x times g prime of x divided by g of x squared, okay? That's the formula that's given. I'm gonna show the problem again, and I'm gonna write the formula again, and show how it's done. Where does this formula come from? Is it thin air? Is it from the book? It comes from how to take the derivative of two functions being multiplied. So this is actually a special case. Okay, so them being multiplied, like I showed in a minute, that's more general. This is more specific, but in the first semester of calculus, you always need to go over this and you need to get familiar with this formula because it comes up so much. Okay, so we're gonna look at both cases and see how it works, but this is the idea. So this is the quotient rule, theorem 8 in the book, and this is how we can take the derivative of a ratio of functions. Okay, that's the idea. So this is going to be posted in the notes after class, but that's the idea. All right. So let me go back to the problem, rewrite that formula, and show you how we might use this. So what is the issue? Let's talk about that. The issue is the 2x minus 5 over the 8x plus 7. I don't know how to take the derivative of it. That's the problem. I'm good with x cubed. I know how to do that now. That's power rule. That's no problem. So the issue is that first term. That's the problem. So how do you take the derivative of it? The textbook says, well, treat it like it's two different functions. Okay. Say that the numerator, that binomial, that's f of x. And the bottom is g of x. Okay. Treat it like it's two different things. The way to take the derivative of this is to follow that formula. So the formula goes, we take the derivative of the first times the bottom one, then subtract the original f of x times the derivative of the bottom function. Okay. And then we're going to take that bottom function and we're going to square it. That's the idea. That's the formula. All right, let's see if we can do this. Take it piece by piece, step by step, and see if we can't build this thing. Then we can do it. Okay. So what's the first part I need? I need f prime of x. Okay. So I know that f of x equals 2x minus 5. So f prime of x, just use power rule. You have 2x minus 5. So the 1 comes down. So it's 2 times 1 times x to the 0th. So that's just the number 2. Okay, so the derivative of f is just 2. All right. Now, what about g? G of x is 8x plus 7 in this formula. And I want to take the derivative of that. So think power rule. If I take the derivative of this, the 1 comes down. It's just 8 times 1 times x to the 0th. So g prime of x just equals 8. Okay, that's the 4 pieces I need to build the formula. Okay, so if that's true, then f prime of x in this example is 2 times the original g minus f of x, which was 2x minus 5 times g prime 8, and then over the original g squared, 8x plus 7 squared. Okay. So I build it piece by piece, brick by brick. That's how I do it. We're in the middle of the problem, but are there any questions of how I got here? Any questions how I took the derivative of those so far? I think the next step would be to try to simplify this where I can. And then we can't forget, we still have to answer the original question. We've only taken we took half of it and took that apart. But let's see if I can't simplify this here. So that'd be 16x plus 14 minus 16x. What was this, 5? Can't even read my own handwriting. That's negative 40, positive 40. Almost. 8x. 8 times 5 is 40, so that'd be positive 40. Yeah, 16x goes away. And so we get 14 plus 40, that's 54. Okay. I've done most of the work, but that's only this part of the problem. Luckily, the other part's really easy. Okay. That is just the derivative of this. And I claim that since they're separated by addition, we can take them individually, and that helps. So this is this part. But I need to remember that we also have x cubed. Okay, let's call this h of x. What's h prime of that? What's under that? The 3 comes down. 3 minus 1, 3x squared. So my final answer is the most of the work. I'd say almost 9/10 of the work was to get that one piece. I get 54 over 8x plus 7 squared. 3x squared. That's my final answer. So almost all of the work was dealing with that quotient rule. Almost everything was that. Okay. But hopefully makes sense. Hey, if you want more practice with this idea, you're gonna love RP. That's where we're gonna go even deeper into it. So I saved a picture of it. And I'm gonna flip through these problems. See what I wanna do. Because I need to go part B as well. Okay. This one's pretty ugly. I want to do it anyway. Okay, I'm gonna do 39 and call part A good. All right. So this is the other issue. Okay, we have what we'll consider a function times another function. We want to take the derivative of that. How do you do that? This is called the product rule, which we're going to use a lot in the next section. Theorem 7 gives us the product rule. Actually, the quotient rule comes from the product rule itself. So this is the formula, and here's what it says. It says that you can take the derivative of the first times the original second plus the original first times the derivative of the second. That is the quotient rule. This one is the easier one to do out of the two, but the quotient rule actually comes from this rule. So if you go later on, it's possible that you would only prove the product rule. You wouldn't have to prove the quotient rule because it comes as a consequence. Okay. So let's see if I can do this. So I want to find the derivative of the whole thing, and I'm going to consider this being a function times a function. So I really need to break this down into pieces to be able to do it, because I can't do it all at once. So I'm gonna say that f of t equals 3t plus 2 over t. And I'm gonna say that g of t equals 7t squared minus 3. Consider them two different things. They're being multiplied. If I follow this formula, if I follow theorem 7, I should be able to get the derivative of the entire thing. So we need to find what is the derivative of f of t here. Well, even that's going to be annoying because it has pieces. But what's f prime here? The derivative of f of t. Use power rule. So for that 3t, that's just going to go to 3. The 1 comes down. The 1 turns into a 0. That's just a 3. Okay. Maybe I'll rewrite this. So 1 is 2t to the negative first. What happens with that negative 1 there? So the negative 1 comes down, it gets subtracted by 1. So minus 2t to the negative 2. I can rewrite this if I want, or I can leave it like that if I want. That should be the derivative of f. Okay. I brought the 1 down, subtracted the 1. There it is. If you want to see how I wrote it in the homework, 3 minus 2 over t squared. Okay, that's f prime. G prime. See if we can find this. So I have 7t squared minus 3. So I bring down the 2. T to the 2 minus 1. Just 1. So I think that would just be 14t. Derivative of negative 3 is just 0 plus 0. So that's 14t. So now I have f prime, g prime. And I can build my formula from there. So let's do it. We're doing f prime times g plus f times g prime. I just have to build it. Okay. So here's the formula. F prime times g, f times g prime. And that would be, by theorem 7, derivative of the entire thing. So f prime I found to be 3 minus 2 over t squared. And then the original g times f, which is the original part, 3t is 2 over t times g prime, 14t. So how do you do it? You don't. You don't take the derivative of this. You take little bitty steps that add up to a result. Okay? Don't take the derivative of the whole thing. No. Identify what you're doing, identify what the formula is, and get your pieces ready for you. Then build it. Okay? Don't try to take the derivative of the whole thing. We'll only make mistakes. And I'm saying it just as much to myself as you, because we are tempted to rush things, but it's too much. It's too much. So make your pieces, put your pieces together. All right. I know I've been going on too long, so let's take a 10-minute break. We'll come back at 3 and we'll talk about part B, which is just more examples of this. I have one other theorem I need to bring up. Okay. So I'll come back at 3 o'clock online, folks, which is in 10 minutes. If you're watching the video, skim.
So I got an email back about me not being part of the class.
Yes.
So apparently it shows that I dropped for non-attendance and that you would need to request that I be added back to the course.
Okay, I will do that after class.
Thank you so much.
Yeah. Online folks, if you could you give me a hi or a hello in the chat? So I know that you're back and it logs participating.
Hello.
Hello. Could you write it in the chat too? Just so it logs. Leader. So we'll start section B. Now, I know there's a holiday weekend here, but it doesn't really affect our class because we go Wednesday to Wednesday. But yeah, so don't let that trip you up on your homework. You still are expected to complete it, even though there was a holiday in the middle. And I would probably try to get it going before the weekend. Things can get away from us. Just wanted to mention that since we only meet on Wednesdays, the holiday, the fact that all the homework will still be due next. Make sure that that's manageable and managed on time. Okay, so the next formula that we need is really not that much more. A lot of what we're gonna do is kind of really dive into the other formulas that we've already looked at. The next one is going to be called the chain rule. So I think of this as outside, inside. You're gonna hear me say that a lot. Outside the function, inside the function. Okay, so we're gonna do a lot of that. Now, what do I mean by outside of the function, inside the function? So let's look at this. So we have y equals 6 minus x to the 63. Okay, I don't know how to do this problem because I don't know how to take something where it has a parentheses and there's an expression inside it. I don't know what to do. So the thought is, if you do a substitution, which comes up a lot in calculus class, if I take the thing in the parentheses and I call that u, then I could say, well, then this is the same thing as u to the 63. And I know how to take the derivative of this using the power rule with respect to u. So I know that dy du by the power rule, I bring down the 63 and I subtract 1 from 63, which gives me 62. So, okay, that's not the answer to the problem, but this is going to be a way of breaking up the problem. So I've substituted the inside with I took the expression, made it into a new variable, took the derivative according to this. Okay. So that's dy du, but that's not what the answer is. And they want dy dx. So the chain rule says if you want dy dx, which we often do, you could take dy du dx. So this is the chain rule. Okay, what on earth does that mean? It means I also have to take the derivative of the inside. So I also have to go du dx. So what is the derivative of 6 minus x? Well, the 6 will go to 0 by that constant. Bring down the 1. You're going to get negative 1x to the 1 minus 1. That's just negative 1. So that's du dx. And that's dy du. So the chain rule really says take the derivative of the outside and then multiply it by the derivative of the inside. So that's what I'm going to do. So I think my final answer, dy dx, is 63u to the 62 times negative 1. But I need to sub back in what u was, because the question had nothing to do with u. I need to sub that back in. So what was u in the first place? 6 minus x. So that's what my final answer is. So 63, 6 minus x to the 63 times negative 1. The only thing that's going to change, negative 63, 6 minus x to the 63. So that's the chain rule. And that's what it officially means. And that's how you break it down. Most of the time we do this, we do not have to be so particular. We can do it a little bit easier, okay? So a lot of times I'll just say, take the derivative of the outside and then multiply the inside. So that being the case, let's look at this problem all over again. So first, take the derivative of the outside. Okay, what is the outside? What do I mean? Take the derivative of the parentheses. So that's 63, 6 minus x, 63 minus 1 is 62. That's the first part. Now take the derivative of the inside, 6 minus x. So that would just be negative 1. So multiply it by negative 1. So the answer for this derivative is negative 63, 6 minus x to the 62. A lot of times we don't have to take it so what are they saying? 63 minus 1. What's Kevin talking about?
On the last problem, you just forgot to have the 62 as your exponent. You had it as a 63. It was the last problem. When you wrote your final answer.
Bears upon 60. Thank you, Kevin and Becky.
Also notice that too.
Call me out on this stuff. I gotta look like I know what I'm doing. I got. So even if you know what you're doing, very easy to mess up, make mistakes. Okay, so that's the idea, is that you can do it by the definition, great. Okay, dy dx is dy du, du dx, but a lot of times we don't have to do it so serious. We can just think of it as the parentheses, take it in respect to that, and then take the derivative of the inside. Or that's when I was in your spot, that's the way I would often think of it. Outside, inside. Okay, it's not until later that the questions or your problems get so complicated you have to do it. And I'll show you those. You have some of those at the end. So we'll look at those, right? So again, let's see what we can do and really bend that power rule as far as it will go without breaking. So we have y equals the square root of x squared plus 9. You hopefully can guess what I'm going to do with that square root. Right even before I do anything, I'm going to convert it to a power. Because I am going to exploit that power rule as far as it will go. It makes everything easier. So if you will allow me that, then I'm going to take the derivative of the outside first, which I'm just treating in the parentheses. So the 1/2 will come down. 1/2 comes down. Leave the inside alone. And I have 1/2 minus 1. Okay, so I've taken the derivative of the outside. Okay, that'll turn into negative 1/2 as the exponent. Hopefully I remember to write it. Now, take the derivative of the inside. So what's the derivative of x squared plus 9? The 2 comes down, the 9 goes away, that's 2x. So that's the answer. I just need to rewrite it as the computer will understand. Okay, so what do we have? We have 1/2 x squared plus 9 to the negative 1/2 times 2x. That 2 over 2, that's going to reduce. We have 2 divided by 2, that reduces. I have a negative exponent, so that can go in the denominator. So I have x over x squared plus 9 to the positive 1/2 if I put it in the denominator. And if I want, I can convert it back to that radical notation. Radicand square root x squared plus 9. That's what I think the derivative is. Okay. Outside, then the inside. Outside, then multiply the derivative of the inside. What the book will say, what the official term is, you substitute it, dy, du, du, dx. But I also want you, because I know how much it helped me, also want you to have practice where you don't need to substitute it, because it's only going to add more work to you. Sometimes we have to. I'll show those problems as well. They're coming at the end. But it's worth having practice of not needing. So derivative outside times derivative of the inside. That's the chain rule. I can't quite remember what my calculus professor, I remember I took it over a summer, between freshman and sophomore year. So I took it that summer, and I remember he said something about a turtle, something about take the derivative of the shell or something. I can't remember what his analogy was, but I remember he saying it go through my head. So there's something about take the shell, the outside and then the inside. Okay? So that's the idea. Okay, so we'll keep practicing that and pulling together the idea. Okay. We want to do this as well, and that should be somewhat similar. We have y equals the square root of 3 minus 5x. My first instinct is to get rid of that square root as fast as I possibly can. So I'm going to exchange that square root for an exponent, because then I can use the power. So I'm going to trade the square root with an exponent. And if I do that, then I can use the power rule. So to take the derivative of this, I'm going to take the derivative of the outside first times the derivative of the inside. So dy dx, the first derivative. Let's bring down that 1/2. Bring it down. 1/2. Leave the inside alone. 1/2 minus 1. And then take the derivative of the inside. So 3 minus 5x, straight line, rate of change is -5. So times -5. So that's the answer. Now I just have to rewrite it. Okay. So that's 1/2, 3 minus 5x to the negative 1/2. Don't let me forget that -5 out there. Then I can rewrite it again. -5 over 2 root 3 minus 5x. Yeah. That should do it. I promise I'm going to go back to examples where I show the substitution later in this lecture. I will go back to that, but I want to practice both styles, and this would be an example where I would just do outside inside. Question. comment, complaint?
Really silly, but where did we get the two again? Where did the two come from?
2 came from 1/2, 1/2, 1/2. There's a 2 in the denominator.
Right.
Don't hesitate to ask me a math question. Don't hesitate. You can always ask me where did a 2 come from. Please don't hesitate to ask something like that. I'm not gonna say it's easy, but I am gonna say with practice, you will be just as good at it as I am, if not better. I'm not gonna say it's easy or interesting or your favorite thing to do. After you get good at it, it can be kind of fun. I won't promise you that, but you can be just as good at it as I am. I have no superpowers. This is gonna be another. So let's take it as it is. Okay, piece by piece, not all at once. I can tell by the answer. So what am I looking at? Looks like it's a function times a function. So right from the go, I think I have something like this and something like this. It looks like it's a function times another function, which is product rule. And not only do I have product rule to be concerned with, but both of those functions are going to need chain rule as well. And chain rule is going to be outside, inside. So we have 2 things going on at once. Okay. Well, let's see if I can walk us through it. Maybe. At least with the help of my friends, if I can. Okay. Well, what was product rule? Let's bring that up first. So product rule. F prime times G plus F times G prime. That's product rule. So that's where I'm going. Okay. But I'm not going to do it all at once. I'm going to take it piece by piece. I'm not going to try to do the whole thing, because that's too hard. So I'll just do a little bit of little. So what's F prime of X? Well, even that is kind of hard, because now I have to do chain rule. First class, we're gonna get through it. Okay, chain rule. So outside, inside. We bring the 4 down. 4 comes down. Leave the inside alone. 3. Then derivative of the inside, 3x minus 5. That's just going to be the number 3. I'm just gonna rewrite this for myself now. I have it for later. So happy that they decided to do it at the beginning of the year and not over summer break. Okay, did I do that right? 4 comes down. 4 minus 1 is 3. Derivative of the inside is 3. 3 times 4 is 12. Okay. G prime. 4 comes down. Leave the inside alone. 4 minus 1 is 3. Derivative of the inside would be negative 5x to the 4th. This up for us. 4 times 5 is 20, so that would be negative 20 x to the 4th. 5 minus x to the 5th cubed. We'll just rewrite that, right? So what am I doing? I want to find the derivative of this entire function. Looks like it's a product of one to the other. So I have to find my pieces. F, F prime, G, G prime. So now, if I did it right, hopefully, through all the distractions of the stomping on the roof, I have my 4 pieces. Now I'm going to do the product rule. That says f prime times g plus f times g prime. So I just have to build it. So dy dx is f prime times the original g now I'm done. Okay. Plus the original f times g prime. It's looking ugly. I have to rewrite this for you guys. So my goal was to write f times g prime. I'm sorry, f prime times g plus f times g prime. Rewrite it for you. 12, 3x minus 5 cubed, 5 minus x to the fifth, to the fourth. It's a plus in the formula, but it's a negative 20x to the fourth, 3x minus 5 to the fourth, 5 minus x. That is my solution, which is ugly, but it's piece by piece, step by step. It's not all at once. It's identifying that I have to use the product rule, and then I have to find my ingredients. Once I have all my ingredients laid out, then I can do it. Okay? I'm not tackling it all at once. Even if I was doing the problem by myself and I wasn't showing anybody how to do it, I'd still take it piece by piece because I'm less likely to make a mistake. Not impossible, but I still will make a mistake, a sign error or so, an arithmetic mistake. But don't try to do it all at once. It's too much. I don't know how to say it another way. Okay. So we got a picture of that. I'll post it after class. And I will move on to a different problem. Okay. Same idea, different function. X times x cubed plus 9 to the fifth. Again, I think this is going to be product rule. I'm going to have to treat them like two different functions. So what if f of x was just x? What if g of x was x cubed plus 9 to the fifth? Okay. So if I treat them like two different functions, then the derivative of the whole thing by product rule be f prime of x, g of x, plus f of x, g of x. That's the goal. Piece by piece, stone by stone, not all at once, little by little. Okay. So what would be the derivative of that f? What is the derivative of x? The 1 comes down, that 1 up top goes to 0. So I think f prime of x just equals 1. Okay. What's g prime? What's the derivative of g with respect to x? Here I'm going to have to use chain rule. I have to use chain rule here. So this is g prime of x. Bring the 5 down. Leave the inside alone to the fourth. And then the derivative of the inside. So it's like a whole new problem. 3x squared. Yeah, 3x squared, exactly. I could clean it up for myself if I care. 3 times 5 is 15. X squared, x cubed plus 9 to the fourth. I'm just rewriting it in case it's easier for me later. That's the idea. So I think here I can build the product rule. Okay, I'm building the derivative piece by piece, stone by stone, not doing it all at once.
Trying to like trying to see.
So it's f prime times g plus f times g prime. Okay, so dy dx equals f prime, which I found was the number 1, times g x cubed plus 9 to the 5th. Then there's a plus sign in the formula. I leave f alone. It's the original f times g prime. Times g prime. G prime is 15 x squared x cubed plus 9 to the 4th. And then I could even clean that up too, because I have x times 15x squared. And I don't really need that 1. X cubed plus 9 to the 5th plus 15x cubed plus 9 to the 4th. That's a better version of it. So that's 2 theorems in 1. It's just, I just can't say it anymore. You can't, you could, but don't do it all at once. Piece by piece. I'm going as fast as I possibly can. I want you to take your time as much as you can. Okay? Don't do as I do, do as I say. I'm trying to show as many examples as possible, but I want you to take your time, identify what you're looking at. And go from there. Of course, review the notes, review the video that I'm inside right now. Hopefully that gives you a head start of how to do this, what to look at. Okay. That being said, let's look at more problems. 11. All right, this one is breaking it down. It's forcing me to break it down. Find dy du, du dx, dy dx. So this is forcing me to break down chain rule. Again, chain rule, outside, inside. That's how I say it. But dy dx is the same thing as dy du dx. Okay, so again, you could substitute the inside, the parentheses part, you could substitute it with a u, then take the derivative, and then take the derivative of the substitution and multiply them together. This one's going to force me to do it. So it tells me that y equals u to the 49th. So what is dy du? Dy with respect to u, the 49 comes down, and it gets subtracted by 1, so that'd be 48. So that's dy du. It says that u equals 3x cubed plus 2x squared. So du dx, just taking the derivative of that. The 3 comes down. 3 times 3 is 9. 3 minus 1 is 2. 2 comes down. 2 times 2 is 4 times x. 9x squared plus 4x is du dx. So the first step was find dy du. Then it tells me find du dx. And lastly, it says find dy dx. Okay, dy dx, again, by chain rule, by the theorem, dy dx is dy du dx. Okay, so what was dy du? 49 u to the 48th. So that's dy du. And then multiply that by du dx. 9x squared plus 4x. But that's not the answer, because the answer has nothing to do with u. It has to do with x. So I need to replace that original u. So this u needs to go in here. I need to sub that out. if I do that, it would be 49, and then the original u was 3x cubed plus 2x squared times 9x squared plus 4x.
Where did 48 go?
Don't know. There it is. I found it. I just had to wipe the smudge off. There it was. It was right there. Just couldn't quite see it. Couldn't see it. Other good questions. Someone else have a good question. I'm going too fast for myself, so
So, will you, or did you upload the chain rule in the announcement?
it is forthcoming. So this will be posted after class, because I'm still building it. Chain rule is right here. But I don't know if that's even that helpful. I don't know. It says that you can think of it as a composite function. That's fine, a function inside another function. It's roughly saying the same thing, take the derivative of the outside and then the derivative of the inside. But it's comparing it to a composite function, which I guess I need to. I guess it makes sense. I try to just show it rather than point it. And then proving that is fine and helpful, but not until you get a hold of what it even says. So I try to show it. And then that doesn't have anything to do with dy dx. But you'll see that as well in the chapter. Okay. Let's see if we can't find this one. I remember this one being hard. Maybe it was just my mind frame at the time. Dy dt, if y equals this and u equals this. So I'm supposed to find dy dt, which is just like dy dx, except it's with time rather than x. So dy dt equals dy du times du dt. We have to remember to sub all u's back to t's. Okay. All right, so I guess first things first, let's find du dt. Let's see what happens. So du dt equals 5. That was easy. So this isn't so bad. It's not editing me. So if I take the derivative of u with respect to t, I get 5. Slope of the line is 5. I also need to find dy du. I think that's going to be the problem. Yes.
You explained already, but could you explain again, like how do you see du or dt?
How do I see it?
Like how do you choose which?
It's saying u. It wants me to find dy dt. So by chain rule, that's my formula I have to find. So I need to find the derivative of u with respect to t. So it tells me that u equals 14 plus 5t. So how do I find the derivative of 14 plus 5t? The 14 will go to 0. For the 5t, the 1 comes down. So it'd just be 5 times 1 t to the 1 minus 1, so that's just 5. So that's du dt. And the hard part is going to be to find dy du. That's gonna be the hard part. But we can do it. And there's two different ways we could do it. One way is we could use the quotient rule, or the other way is we could change the exponent and then use the chain rule again. So I will let you choose. I will let the audience choose. Chain rule or quotient rule? What do you want? Quotient rule?
Yes.
Okay, so let's do that. So just to be clear, I'm looking at y equals 1 over u squared plus u. And I want to take the derivative of this with respect to u. There's a ratio there, so I need to do the quotient rule. What was that? F prime is g minus f times g prime all over g squared. That's quotient rule. So I need to do that. Okay, so I think f is 1. That's the easy one. And I think that g will be that u squared plus u. So let's see if I can do it. So if f is 1, the derivative of 1 is 0.
It's 1.
Yeah, I'm gonna say for the quotient rule, the f of u is the number 1. So f prime of u equals 0.
F of u, how do you find it?
It's the top one. It's the top function.
Oh,
Because we were gonna do quotient rule, so top over bottom. So I think that's 0. So dy du would be 0 times g. That's just gonna go to 0. I'm gonna get rid of that. Minus f, which is the number 1 for this example, times g prime, 2u plus 1. All over g squared. And then I can clean that up. Minus 2u minus 1 over u squared plus u squared. I'm starting to remember why this was a hard problem. So this is the fork in the road. You could use quotient rule or you could have used chain rule. We chose quotient rule, and we're just gonna keep going. So that's dy du, I'm pretty sure. And from there, I need to build dy dt. So dy dt is dy du times du dt. The nice thing is, du dt is just the number 5, so at least that's easy. At least I have that in my favor. So dy dt equals dy du du dt. Okay. So dy du, it's this guy. Negative 2u minus 1 u squared plus u squared. And then du dt was 5. So we multiply the whole thing by 5. Even I can do that. So that's easy stuff. At least we got a break somewhere. Now I have to keep going because all my answers in terms of u and the questions in terms of t. So I need to replace all u's with those expressions. And so it's just an algebra problem at this point. Calculus is done. We have done the calculus. We've taken the derivative. Now we are doing the algebra part. We are subbing in the variable. So negative 2 times 14 plus 5t minus 1 over 14 plus 5t squared plus 14 plus 5t squared all times 5. I have, do we go to 45 or 50?
Good, 50.
Okay, I'm gonna need all 10 minutes to go over this somewhere. So I'm gonna leave this problem here and you have the solution. I manipulated the variables and reduced where I could, but I'm going to leave it here so I can show more problems. Okay, calculus is done, now it's left with algebra, and there's an example problem. I did have to move variable and cancel things out, that kind of thing, so because I only have 10 minutes left, I'm gonna move on. Calculus is done though. 17. I'm sorry I go so fast. What else could be done other than showing us problems? If $1,000 is invested with an interest rate of I, compounded annually, in 3 years, it will grow to the amount given by A equals 1,000, 1 plus I to the 3. Business folks, you guys know this interest rate, this is annual interest, right? Well, we're gonna do some calculus on annual interest, okay? What's the rate of change with this? So it looks like it's 3 years, that's where the 3 comes from, so it's 3 times 1, since it's compounded once a year. We're gonna find the rate of change. How do you find that? So you want to find dA DI, rate of change, the rate of change for the account in terms of interest rate. Okay? Chain rule right here. So we want derivative I, we need to do the outside first. So this would be 1,000 times 3, 1 plus I, 3 minus 1 is 2. So I get 3,000 times 1 plus I squared. Why did I do that? I think I'm getting a little tired. 1 plus I squared. That is the rate of change with the account in terms of the interest rate. Interpret its meaning. DADI is the rate of A, the account, due to the change in the interest rate. So it's with respect to interest rate. It's that. I assume business folks, you have to do interest rate problems a lot. And now you're doing it here too. Taking the derivative of that. That 2 doing there. Problem 19. D squared y over dx squared. What does the 2 mean? Second derivative. Take it twice. This is the second derivative. What does that mean? It means you find dy dx and then you take the derivative of that. You have to do it twice. That's the second derivative. There it is. Okay, so we want to find the derivative, first derivative. Okay, dy dx. If I rewrite that as x to the negative 7th, then the first derivative would be negative 7x to the negative 8. That's the first derivative. But d2y over dx squared is the second derivative. So now I'm going to take the derivative of this. What's the derivative of this? Once more, negative 7 times negative 8, x to the negative 9. So I bring the 8 down, x to the negative 9. Okay. And we could keep going, but it only asks me for the second derivative. But I could easily find the third, fourth, fifth. You just have to keep going. Okay. 7 times 8 is still 56. x to the negative ninth, I can rewrite it as 56 over x to the ninth. That's what the second, that's how you find the second derivative. Derivative of the derivative. Okay, derivative of the derivative. That is your acceleration if you're talking about the speed of an object. Okay, the rate of change of the rate of change. Sales are going up and it's speeding up. So that's growing, slowing down, that kind of thing. So that's the acceleration is the second derivative. Okay. I have 4 minutes left. Can I do a good problem? Can I pick a good one? That one's not terrible. I'd like to pick, I'm gonna pick this one because it's asking for the fourth derivative. Okay, a chill. A chill goes throughout the fourth derivative. Let's do it. So dy dx of this function would be 7 times 5 x to the fourth. Okay, that's the first derivative. So that's 35 x to the fourth. And now I want to find the derivative of that. Okay, so then that's bring down the 4, which is 120, 140. He says, yeah, to the third. Okay, the third derivative is the derivative of that with respect to x. So the 3 comes down. And it wants the fourth derivative. So that's 840. Fourth derivative is the derivative of the third. First derivative, if you're talking about an object, first derivative is its speed. Second derivative is its acceleration. Third derivative is called jerk. It jerks and then accelerates. That's the third one when you find it. And I don't know what the fourth derivative is called. I don't remember that one. But I could keep going mathematically until I run out of stuff. But that's it. Question? Comment? Concern?
I'm
Complaints?
a little fast, but I'm gonna watch.
Oh, yes.
The class.
Derivative of the derivative of the derivative of the derivative. So I'm just taking the derivative over and over and over again.
I just got done writing the first one down.
Let me also mention this. This is how the class should be taught. Chain rule should have been 1 lecture. Product rule is 1 lecture. Quotient rule, 1 lecture. Second derivative and probably applications would be another lecture. You had this all at once within 3 hours. Talk about way too fast. It's like a month's worth of work in 3 hours. Okay? So it is too fast, too much, no question about it. But the only other option I have is to show you less and expect you to teach yourself more. And I still didn't get through what I wanted to do. And I only wanted to do 43% of the homework. So what does that mean? It means get started early, emailing me questions early. Get stuck fast. Get stuck tomorrow on a problem, okay? Email me your homework questions. I will make videos and send them back to you as fast as possible. The best way you can do that is not wait until Tuesday evening. Okay, get started early. I know it's holiday weekend. It is for me too. I also have a family and I also have another job. So I am also busy. But never hesitate to ask me a math question at all. You are not bothering me. Ask me. I don't understand problem 29. I tried, it doesn't work. I'll help you. Okay, that's the goal. Okay. All right, that's my time. I will stay for questions. But please have a safe Labor Day weekend. Get